Alrighty, let's see. Okay, that's going. Ready, good morning. Oh, this is not for us. We have more reactions today. Hooray! But as you guys had asked, as we go through this, I think is this the right one? Yeah. So I have a textbook that I wrote for basically Chem 101, the equivalent thereof. So I have some videos. Here's my hand. So this is an example of a double displacement reaction that has produced a precipitate, which is going to be lead to iodide. That's that bright yellow thing. And we can tell it's a precipitate because it's cloudy, right? We can't see through it very easily. And if we were to wait several hours, we would see that this one is going to settle out later. All right, here's another one. Here's a neutralization for you guys. Here, let's make it big. So I don't know if you can see this, but you see the steam and you can see the temperature rising pretty rapidly. That's pretty common in a neutralization reaction. So that's going to be an acid-base type 1. Let's see. Aha! Acetic acid and sodium bicarbonate. In they go. Look at all that gas coming out. So notice that these are really quick. Let's see, what's this one? Oh, we're going to have a single replacement one. This is one we're going to do today. So this is a solution of silver nitrate that has a piece of copper in it with some bubbles that got trapped. And so we're going to see over time, this is sped up, of course, that we're going to see that we're going to get silver metal out of this. Why no gloves? And I'm a chemist. I don't need gloves for this. But I did wear goggles. And so you can see that we have this lovely blue solution, and we have now our copper film covered in silver metal, which is fun. And it's dripping all over the table, causing a huge mess. And now you can see it's blue. By the way, if you could, so blue is actually the color that copper 2+ ions look like. Sorry, I dropped the paper there. Let's see, do I have any other fun chemical reaction videos for you guys? No, I don't think I do. So, okay. So at least those are ones that are there for us right now. So, what am I doing? Back to this thing. Okay, cool. Good morning. So yeah, so there are some demonstrations of what that stuff looks like. You know what? Here's another one. Let's just do it for fun. I will have to find it. So in the meantime, while I am doing so, why don't you guys do you guys have any questions for me from what we did last time? Ooh, let's see. Where is this going to be? I think it's in chapter 4. No, that's boring. Anything at all. Of course. Maybe it's this one. I honestly do not remember where we have put the video of sodium exploding. Let's see, where else could it be? Could be in here. If not, I'll find it later and let's see. Come on, sodium. Let's see, I think you'll be in this chapter. Any questions on double displacement stuff from before? Okay, forget it. I give up. Okay, I'll try and find that video for you guys later so you can watch me blowing stuff up. in a bit. Okay, anyways, back to chemistry. So, okay, cool. So, let's see. We did double displacement last time, right? So, let's do a warm-up one. Let's do that. Oops. This is the one that produced that bright yellow powdery thing that we saw. So, do this reaction for me. Finish it, balance it, state of matter it. You can throw down a net ionic equation too if you like. That would be nice. But also, just so you guys know, like these things, the lead 2 nitrate and the potassium iodide are totally like not harmful at all. So that's why I didn't really need to wear gloves for those. However, for the acid and base one, I probably should have, because I think we use 6 molar for those. But that's neither here nor there. Okay, cool. What are the products? Someone tell me. Do it before Kevin gets the answer right. Now Kevin beat you guys to it. And we'll just throw that in there too. So, important to notice, is that the charges don't change. In double displacement reactions. I guess I should write that out because you guys will not remember what DD means. Double displacement. Okay. If you were to do a net ionic equation, by the way, it would be you would see that the potassium and the nitrate would be spectator ions, and we'll get rid of those for our net ionic equation. So, hopefully nothing too crazy there. And we learned all our solubility rules and gas predictions and all that stuff. And I gave you guys homework because we love homework. I gave you 2 assignments actually. And I'll give you another one today because why not? You love homework. Yay. I know it seems like a lot of homework, and it is, but this is also a 5-unit class, so like you're getting a lot of credit for it, so there's a lot of work associated with it. Now, some of this is stuff we would probably have done in class in like groups and stuff, but class is not existing, so oh well. Alrighty, so we're going to learn another type of reaction now, which is called single replacement, aka substitution. And so how this is going to look, since I showed you that video, we saw that we had silver coming out, right? We know that we produced silver, and we know that we actually had formed copper ions because the solution turned blue, right? It was clear to begin with, and it turned blue. We have evidence that this stuff happened. So we're able to see that what's happened here is that copper has come into this compound, has seen silver nitrate, has kicked out the silver, and has kind of stuck itself in there instead. So it's replaced or substituted itself into that compound. You'll always be able to recognize a single replacement reaction by understanding that you have an element plus a compound turning into an element plus a compound. So in this case, we have copper is the element on the reactant side, and the silver nitrate is the compound. And then after the reaction, we had silver as an element and copper 2 nitrate as the compound. Notice that copper went from a charge of 0 to a charge of 2 plus. And silver went from 1 plus to 0. How do we know that silver was 0? Well, silver ions are invisible to us. And we know silver metal is that silvery stuff, right? We were able to see it on that, that was coming out. We were able to see the silver metal in there. And we noticed that we had copper metal, which we also know that looks like. That turned into copper 2 plus because we saw that it turned the solution blue. Copper 2 plus ions are blue. Silver ions are clear. They do not have a color. And so, if we were to balance this, by the way, that's how we would do it, we would see that the overall reaction here, if we were to do the net ionic equation, understanding that our states of matter were these, how do we know the copper was solid? We saw it, right? It was a strip of copper metal, it was that shiny coppery colored metal that we put in there. We all know that most elements by themselves are solids. Almost all metals are specifically. So copper and silver being metals, those are going to be solids at room temperature. So if we were to do the net ionic equation, we would see that this is what's happening. Throwing in our states of matter. So one thing to notice about spectator ions is spectator ions must be the absolute same. So silver ion is not the same thing as silver element, right? 2Ag plus AQ is not the same thing as 2AgS. Those are different, so you cannot cancel them out. And the same with the coppers. So overall, we can see what's happening here, right? And if we were to think about this, okay, we have an ion becoming an element and an element becoming an ion, right? And so what's happening here is electrons are moving from copper to those silver ions, right? So the silver ion is missing an electron, right? That's why it's positively charged. After the reaction, it has gained that electron back. And as a result, copper has lost its electrons. And that's why it's now a positive ion. All right, we're going to see that this is what's called a redox reaction, which means electrons are being transferred. But we're going to come back to that in a second. Tyler, on the reactant side, silver is positive. Do you mean the product side? Okay, good. Yeah, so on the product side, we saw that in the video, right? So I think this was just a ploy to get me to show you the video again. But I will humor you. Let me just go to chapter 9. Okay. You have convinced me to show you the video again. Okay. How do we know we had silver metal? Boom. There it is. We see it. Ah, well then there you go. That's how. So if we can see here, we see that we have silver metal. That's that shiny, sparkly, Christmassy looking stuff that's in there. That's how we know it's silver metal. However, understanding how single replacement reactions work is going to give us the same information. Single replacement will always give us a product that is an element. That is an elemental form. That means it's not charged. So let's do a couple more examples. Let's say we had the reaction that I didn't show you here. So what's going to happen here? Look, element and compound. In this case, I'm going to maybe write, just to remind you, that water is the same thing as like H plus and OH minus. If we want to think about water that way. If we think about it, in water, which one of those is positive? I guess I just said it, right? We want to think like this one's the positive, this is the negative part of water, if we wanted to think about it this way. So sodium, being a metal, is going to want to become positive, right? And so what's going to happen here is we are going to end up making sodium hydroxide, and we are going to kick out hydrogen gas. Remember also, just in case you've forgotten, these 7 elements are always diatomic in reactions. By themselves. So if they're by themselves, those 7 things are always paired up. So that's why we have H2 and not just H by itself. Okay, so what's going to happen here? The sodium has kicked out a hydrogen. If we were to balance this, 2 waters also. Yeah. Okay. That's what's going to be happening here. So we're going to see that overall what's happening, we're having sodium become a sodium ion, and we're having hydrogen ions becoming elemental hydrogen. So we can see the electrons are going from sodium onto hydrogen, producing hydrogen gas, and therefore leaving the sodium as an ion. Another one. So remember, in single replacement, we're always going to have the element kick out the other element, right? So if we look at this, our element here is a non-metal, right? So it's going to kick out the non-metal of the compound. And so what you're going to get is that kind of substitution. Remember that chlorine likes to have a -1 charge, right? So it is going to want to bond with sodium. Here's some balancing for you guys. If you were to do the net ionic equation, you'd see 2 bromines plus chlorine turns into 2 chlorides plus bromine. And you, oh no, the video is glitchy. like laggy. We had some problems with that in the earlier class. My internet was sucking. However, right now it looks like um, Twitch for me is displaying a um, green thing, which means nice. So, um, sorry. Oh no. Okay, well, worst comes to worst, YouTube it after. So, yeah. Okay, well, then it's I don't know what's happening. Alrighty. So, um, let's see. So yeah, there we go. So in single replacement reactions, you're going to have metals basically replacing other metals and non-metals replacing other non-metals. How do we know bromine is liquid? Okay, periodic table time. Although this periodic table does not seem to show it. No, I'm not going to pay for you. Go away. Oh, this one doesn't show it. Okay, let's see. No. Okay, well, in that case, let me pull up another one. Does this one have it? Yes. Okay. So if we go to this handy dandy website here, is it? Hold on. Let me add that as a window capture. What do you mean different for transition metals? Oh, go away. I don't need to see this. I want. Really? You're not going to show me like freaking. No? Okay. Oh, yes, there it is working. Hooray! Okay. So, notice here. So this is one of the periodic tables that one of your colleagues had posted in Discord. Very useful one. So we see there are two elements that are blue. Bromine and mercury. That means for us, elemental bromine and elemental mercury are going to be liquids. The ones that have red letters are going to be gases. So that's all the noble gases, fluorine, chlorine, oxygen, nitrogen, and hydrogen. And then everything else is going to be solid. So that's how we know bromine is liquid. So whenever you see elements just by themselves, they're going to adopt these particular, what are they called? States of matter. So this periodic table, this ptable.com, very useful, especially later when we get into electron configuration. You're going to have all of them here for you. It's going to be very nice and happy and all that stuff. But right here, this stuff is useful for us. So solid, liquids, and gas, right there. Okay, so that's how we're going to know. Okay, so with regard to your question about transition metals, yeah, it's a good one. So transition metals are going to typically. I'm just going to go back to this again. Let's see. Activity series of metals. I don't know what this is. Some random website. Yeah, here we go. We're going to see that there is a kind of people have done this math for us already, where they're gonna list like the most likely metals to kick out other metals. So that hsptable.com, Tyler, easy. I can put that in there. Easy. So there's that. In this particular one, the activity series is also something that you would be given, and it's going to tell you like what's going to be able to react with what. So we haven't covered oxidation yet. That's something we're going to talk about in like 20 minutes or something. So we're going to come back to this table, for example, and then we're going to see how that's going to work. Okay, so I'm just going to switch back here. What's the chemical equation on the bottom for? This bottom one here, this is the net ionic equation. And that's just showing like exactly what's happening. So, the top equation here is what we are typically used to seeing. But if you were to just look at exactly what's happening, when we're talking about oxidation numbers, this is going to be useful for us. The net ionic equations are going to be nice and useful for us. Okay. So, one more thing to note for substitution reactions. If a metal has a variable charge, actually, you know what? The activity series is going to take care of that. So never mind. We will not worry about that. Don't even think about it. Okay, cool. So let's go back to this kind of idea of electron transfer. So we see, again here, the bromide is going to be giving electrons to chlorine to create chloride and bromine. Just like before we saw that sodium is going to give its electron to hydrogen, so on and so forth. These electron transfer processes are going to be called those redox reactions, which involve what's called reduction and oxidation. And so that's where the word redox comes from. We're going to see that reduction means gaining electrons, and oxidation is losing electrons. So, we're going to see that these two processes happen together. You're never going to just have reduction by itself or oxidation by itself, because you can't create matter, right? Electrons are matter. You can't just say, okay, I'm going to throw in 3 electrons at this, this ion, and now it's going to become aluminum, whatever. You have to have something to lose electrons in order for something else to gain electrons. And so, if we take a look at, what was the first one I did? I think it was silver reacting with copper. We can see here that it's obvious for us when there are ions involved, but we can see that one of these is going to gain electrons and one of them is going to lose electrons, right? So which one is going to be gaining electrons here? And which one's going to be losing? Yeah, so silver is gaining electrons, and as a result, copper is losing electrons, right? We can also say silver is reduced and copper is oxidized. Yeah, exactly. So as always, Kevin is already one step ahead of everyone else, which is awesome. So we're going to see that this the gaining of electrons is the reduction. So silver is being reduced and copper is being oxidized. One way to remember this is we can think about oil rigs. Oops. Oxidation is losing electrons. Reduction is gaining electrons. So we see OIL-RIG, oil rig. That's how you can remember which one is which. So oxidation is losing electrons. Reduction is gaining electrons. Okay, so that's your happy Mnemonic, that's what the word is, yeah. Cool. So, if we take a look at our other one, we had we had this example, right? Which one is oxidized and which one is reduced? So again, just identifying where the electrons are coming from and where they are going. So oxidation, which one is losing electrons? Now, Kevin, you've written the same thing for both of them. So, double check that. Something has to be oxidized, right? They can't both be reduced. So if it helps, we can write the charges under these. There we go. That's what I want to see. So we see that bromine is going from -1 to 0, right? And so that's going to be losing an electron, right? It's becoming more positive. That is going to be the bromide, right? And the one that's reduced, therefore, is the chlorine. You can always think of reducing also as becoming more negative, right? It's what we're going to call oxidation number is decreasing. So in this case, it started at 0, neutral chlorine, and became -1. That number has reduced. It's gone down. So that's how we can remember it. All right, we have one more bit of naming or vocabulary here, which is, if I'm going to put the whole equation back up, we saw that bromide was oxidized, right? And chlorine was reduced, right? We saw that already. So if something is being oxidized, that is to say, if something is going to be taking away the electron from bromine, we can talk about that as well. We have words for that. And if something is going to be reducing something else, we have words for that. So we're going to see we have what's called an oxidizing agent and what is called a reducing agent. And so the oxidizing agent is going to be what oxidizes the something, and in doing so becomes reduced. So remember, oxidation, losing electrons, right? That's the same way as saying the other thing is taking electrons, right? I can say I'm losing electrons. Let's see. Let's use Gumbo as our brave volunteer for the day. So I have here an electron. Okay, I could say I'm losing my electron to Gumbo, who just dropped it. He lost his electron too. So I have now lost my electron, and Gumbo has now taken my electron. So I have been oxidized by Gumbo. Gumbo did the oxidation. So he has taken away my electron. And so we have a word to talk about that. The one that is taking the electron is going to be your oxidizing agent. And the one that is going to be giving the electron is going to become oxidized itself, is going to be your reducing agent. Now Gumbo's like, where's the rest of the treats? I know. Well, think about it. It's kind of like in English you have active voice and passive voice, right? Like, I kicked the ball, or I could say the ball was kicked. Like, it's just rephrasing it. So, the oxidizing agent in this case, it's the one that always becomes reduced. So that's going to be chlorine. Chlorine is our oxidizing agent. It is the one that is going to be taking the electrons. And the one that's giving the electrons is going to be the sodium bromide, which is going to be giving the electrons. One thing to notice, agents must be reactants, and you typically you name the whole compound. So that's why we're saying NABR is going to be the reducing agent. We just say the whole compound, that's the convention there. So I know, confusing, because it's the opposite. Aren't we evil? Yay, chemistry. Let's do another example. Let's go back to our copper, silver nitrate, and copper example. So, we saw that silver was oxidized, right? No, silver was reduced. Silver was reduced, I'm sorry. Yes. Silver was reduced, and therefore, silver nitrate is the oxidizing agent. And we could say we know that copper was oxidized, and therefore copper is the reducing agent. So notice, because copper was by itself already to begin with, we just label copper as the reducing agent. But the silver that was part of a compound, we still have to name the entire compound as the oxidizing agent. And again, we always talk about reactants only. We're not going to worry about products for naming what the agents are. Okay, so with that in mind, let's go back to our sodium example. H2, sorry. Tell me what the oxidizing agent and reducing agent are here. So just so we remember sodium went from 0 to +1, and hydrogen went from +1 to 0. And so Kevin has said, it was Kevin, okay, who said that sodium is the reducing agent. Okay, he's saying that because sodium was oxidized. And so therefore it's the reducing agent. And Star-Lord is absolutely correct that water will be our oxidizing agent. It is the one that is going to oxidize sodium. Okay, and in the process, water will be reduced. Okay, so again, it's just semantics. I apologize for it being terribly confusing, but that's my favorite thing to do. Just apologize and be like, well, not my problem. So, sorry. Alrighty. Don't worry, you will have homework on this. Aha. So Shane, it has to be a reactant. Agents must be reactants. NaOH is a product. So that's why. Alrighty. So we're going to learn what are called oxidation states or oxidation numbers, which are essentially electron accounting. You never thought this would be a counting class, did you? Ha! Tricked again. We're going to learn we have rules for determining what the oxidation numbers are. So far, it's been pretty easy for us. We've already gotten the first 3 rules down. We already know them. We know already any element by itself has an oxidation number equal to 0. Let me just write ox number. That might make it easier. Any element that says by itself in its normal periodic table form will have an oxidation number equal to 0. So for let's just go on to the next rule. For simple ions, the oxidation number equals the charge. And so that's one way to think about these. We saw that here are some simple ions. Simple ions meaning they're monoatomic. Remember, monoatomic, one atom. The oxidation number here is +1. For calcium, it's +2. For iodine, it's -1, and for nitrogen, it's -3. These are the oxidation numbers. We already know this. We already know what the charges are for these atoms. Alrighty, here we go. Third rule: for a compound, the sum of all oxidation numbers must equal 0. Again, we already know this. Here is a compound that we are familiar with. If we understand that for simple ions, the oxidation number is equal to the charge, we know that sodium is +1, chloride is -1. 1 minus 1 equals 0. Hooray! Or for calcium chloride, we know that each calcium is +2, each chloride is -1. So let's just double check. Let's see if this is true. Do we have 2 minus 2? I'm sorry, the sum of all of these things must equal 0. Sum. Right, so 2 plus 2 times -1. Does that equal 0? You bet it does. Just to make the previous one more clear, I'm going to write it as 1 plus -1. Just so that's super clear for everybody. So we have to make sure the sum of all of these equals 0. So far, we have already done all this stuff. This is charge balancing. You guys already know how to do this. The last one is when all else fails, try doing these 3. In this order. And so these rules are hierarchical, which means rule 1 takes precedence over rule 2, over rule 3, over rule 4. So if you are going to break one of these rules, break one of the higher up ones instead. So let's see what this means. So for ionic compounds, it's easy for us to assign oxidation numbers because we know that rule 2 is telling us that for simple ions, the charge is the same thing as the oxidation number. But here we have a molecular compound, right? It's a covalent compound. It does not have charges. So what we must look at is, okay, is this an element by itself? No, it's a compound, right? So rule 1 does not apply. Rule 2 talks about simple ions. This is not an ionic compound. We do not have simple ions here. And so this tells us, rule 3 says, the sum of all of these numbers must be equal to 0. So that's telling us that carbon plus 4 hydrogen must equal 0. And so we don't have any information, so let's keep looking. So rule 4 tells us that fluoride should be -1, and then hydrogen should be +1. And so if we do that, if we substitute in +1 for hydrogen, we're going to end up getting that carbon is -4. So the oxidation numbers here are -4 and +1. Again, these are not charges. This is not an ionic compound. We do not actually have carbon 4- and 4 H+ along with it. However, we're going to use these numbers to do some determinations. Let's look at another couple of examples. Let's see this particular one. So just like before, not an ionic compound, so we don't have simple ions. We know that we have, just to make this clear, that's a 0. This first one's an oxygen. We have to go ahead and look up, so we don't have any other rules, so it's telling us, okay, first fluorine, then hydrogen, then oxygen. So oxygen should be -2. So C -4 equals to 0. So C in this case is +4. And so what we're going to see here is those are going to be our oxidation numbers for this particular compound. Last one. Not an ionic compound, so we know that 2 hydrogens plus oxygen must equal 0. We go to our rules. Hydrogen comes first before oxygen. So 2 times plus 1 plus oxygen equals 0. 2 plus oxygen equals 0. And therefore oxygen equals -2. Algebra. And so these would be the oxidation numbers for water. So what the heck's the point? Let's do it. Boom. Here we go. We've seen this before. A combustion reaction, yes? Let's take a look. Oh, we've already done the oxidation numbers for all of these guys, except for one of them. Oops, I'm sorry, it's the opposite here. Shame on me. Shame, shame, shame. Looking at this, what's the oxidation number of O2? And while we're doing this, I'm just going to make a little table. Aha! Is this -2? Aha! I would agree with our second classmate here. It's actually 0, right? Elements by themselves must be 0. So we're going to kind of make a table like we did for balancing. So this is slightly different. Let's just look at the oxidation numbers. So carbon is going from -4 to +4. Hydrogen is going from +1 to +1. And oxygen is going from 0 to -2. So as soon as if any oxidation number, I'm sorry, I will be consistent with my abbreviations. We have a redox reaction. And a redox reaction must have reduction and oxidation. So we're going to be able to look at this and say, okay, what's oxidized? What's reduced? What is the oxidizing agent? And what is the reducing agent? So let's see. Carbon has gone from -4 to +4 in terms of oxidation number. So what does that mean? Has it effectively lost electrons or gained electrons? So we're saying O is oxidized. What does oxidized mean again? Oxidized means losing electrons, right? So if it's gone from 0 to -2, is that gaining or losing electrons? Yes. Yeah, it's lost electrons, right? So you can say here, oxygen is reduced. Right? It has become more negative. Yep, totally understandable. It is very common to switch these, especially with the agent thing messing us all up. So that's what practice is for. I have plenty of practice for this for you guys. So we'll have that. Okay, so which element is going to be oxidized then? Which one is going to be losing electrons? Yeah, carbon, right? So carbon's being oxidized, oxygen's being reduced. So our oxidizing agent, therefore, the one that's reduced, is going to be oxygen. So we go up here and look at which reactant oxygen is a part of. And so our oxidizing agent is going to be O2. And the reducing agent, as Tyler has said, is going to be CH4. Correct. Hydrogen has remained the same. So hydrogen is not being oxidized or reduced. That's okay. So that's why hydrogen does not go into the oxidized or reduced little table that we've done here. And yes, indeed, methane is going to be our reducing agent. So we can do this stuff for molecules as well as ionic compounds. So for ions, it's fairly easy. It's just the same as the charge. But when we throw in more molecular compounds, we can do the same thing. Best part about these, for figuring out the oxidizing and reducing agents, you don't need to balance your reaction. So you can save some time there if you're doing that. Let's do another one. Oh gosh, what happens with the iodine? Oh, it's ICl, that's right. Okay, cool. Crazy reaction for you guys. Don't try to balance it. It will be a huge pain in the ass. By the way, HCl ends up with a coefficient of 25. So that's why you don't want to balance this. Don't even worry about that. Let's look at the oxidation numbers. So there's a couple of these we can do right away. For example, water we already did. Same as before. We have a couple of ionic compounds here that we can take care of. Which compounds are ionic in this reaction? What's ionic here? I would say HCl could be considered ionic. That's fine. We can do that. However, ICl is not ionic. It is a capital I. Wait, oh, you mean HCl? No, it's not HCI. It's that's why I do capital I's like that. So it's not carbon and iodine. Yeah. This guy is ionic, and this guy is ionic too. Right? We have metals and non-metals there. So simple ions will have. Ooh, look, we have our first crasher. How awesome! How exciting! Let's see. How the hell do I ban this person? Well, whatever. We'll deal with them. Let's give them chemistry to do. Okay, cool. So, exactly, right? Just ignore that one. I will put a bot in to get rid of them. But yeah, we don't have to worry about that. Okay, cool. So we only have two compounds in here that we actually have to do our oxidation numbers for. Oh dear, and I've already have come up with a problem, but oh well. Okay, HiO3. That's one we have to look at. So we're going to know that They should all add up to 0. And so we know that hydrogen is going to be +1. And we see that oxygen is going to be -2. That's going to be on our rules here. Rule number 4, for when all else fails. I guess I should continue this because we're going to need it. But, God, I didn't want to have to do this. But here I am inadvertently giving you a problem that has this sort of thing. Okay, anyways. So all this stuff has to equal 0. So whenever we have something like this, we always have to solve for the last one. We can't say right away that iodine is -1, because if we do that, it's not going to equal 0. So we're going to have violated our third rule, which is not allowed. So if I do this stuff up, +1 plus iodine -6 equals 0. Iodine, therefore, is +5. +1 plus 5 minus 2. Why would you balance it? That's just so awful. I mean, you did it. That's great, but what a pain in the ass. Or maybe you looked it up. That would be an easy way to do it, right? But yeah, that is the correct balancing of this equation. Should I have given that one to you on your exam? You guys could balance that, right? Yeah, right. No, not for this stuff. You do have to balance it if you're asked to balance it, or if you're doing like stoichiometry. But let me get to that one in a second. With oxidation numbers, we do not need to balance it. Does not matter. Okay, cool. So why did we isolate I again? Because rule 3 says that everything has to equal 0. We always have to solve for our last one. So in this order, for rule number 4, we have to apply them in this particular order. If we just said, okay, I is -1, if we were to try and do that, if we say, okay, +1 minus 1 minus 6 equals 0, does not work. So we have to always do them in the order that rule 4 says if we need to. So rule says fluorine first, then hydrogen, then oxygen. Those are ones you'll plug in that order until you do not have any more left. Okay, so not going to work if we plug in -1. And so for ICO, we're going to have I plus Cl equals to 0. If we go ahead, I know I just stuck those on because I didn't want to give you a problem like this, but I did. Chlorine will take precedence over iodine. And so iodine is going to be +1. So if we go all the way back up, use the right color. Oh, we have finally done it. Oh my goodness. Let's see, we had H, I, O, F, E, and Cl. We had all of these elements in here, right? If we look on the reactant side, our hydrogens were both +1. And on the product side, they're also +1. Sorry that I keep having to scroll up. Iodine on the left is +5 or -1. And then it has gone to +1. We're going to see what this is, don't worry. Oops. Oxygen is -2 on both sides. Iron is +2 on the left, +3 on the right. Chlorine is -1 on both sides. So if we look at this, we see that iodine has gone from +5 to +1. Iodine has also gone from -1 to +1. And iron has gone from +2 to +3. The others have all stayed the same, so I'm going to ignore them. So, what's happening in which one? We can see if it's going from +5 to +1, that is reducing, right? That number is getting smaller. It's gaining electrons. So we can say iodine is reduced. We can also see, okay, iodine is also going from -1 to +1, different iodines. They're in different compounds, right? So iodine is oxidized. And we can see here, yeah, iron is also oxidized. As long as you have one of each, that's a redox reaction. It is totally okay that we have two things that are being oxidized here. That's not a problem. As long as we have one reduced, one oxidized, we can have as many as we want of the rest of them. So those are the things that are oxidized and reduced. So that being said, let's look at the compounds that this comes from. So the iodine that's being reduced was +5, right? And so let's go back up to our reaction. Where was iodine +5? Aha, that's up in this compound, right? That's where iodine was +5. You flipped them. So this tells us that the oxidizing agent is HiO3. One way you can always kind of remember this also, typically oxidizing agents have a lot of oxygen with them. That's one way you can cheat a little bit. Typically oxidizing agents have oxygen with them. Just like in our in this one before, we had the same idea, right? So that's what's going to happen there. And both of these are part of the reducing agent, which is FeI2. So we saw that where iodine was +5, that's the iodine that was being reduced. So therefore, that is the oxidizing agent. Because the iodine 5+ was reduced. I don't want to say 5+, that's not an actual charge, but the iodine of 5+. And then in purple, this is because Fe and I were oxidized. Okay, and so that's why it's the reducing agent. And that's why this one is the oxidizing agent. The one that is reduced is part of the oxidizing agent. The one that is oxidized is part of the reducing agent. So that's how that works. Oh wow, we've really gone over time, haven't we? Shame on me. My bad. I'll give you practice on this. It's exciting. We have one more thing to do in this chapter, which will be concentration and some solution stoichiometry. So we'll do that on Monday. Tomorrow is our test review day. Because I am asking you to kind of do a correct your test as an assignment for just as I try to predict this, I want you guys to maybe try and cap yourself as 1 or 2 questions for tomorrow, just so I'm not doing your homework for you, as it were. So maybe try and choose the hardest ones to ask me to do, and then you can do the easier ones yourselves. By the way, something super cute is happening down here. See if you guys can see it. That's Oz and Gumbo smished together to form some some sort of new compound together. Those two are father and son, by the way. So it's just extra cute, I guess, that they're the ones who are squashed together. So, and just look at how much bigger Gumbo is. Yeah. So, okay, cool. So we'll continue on Monday. I'll put up some practice for this, as well as the homework thing. So the practice will be kind of a check your own answer. So kind of like that balancing reactions practice that I put up. You kind of will create your own quiz and do some practicing. Yeah, right. They're yin yang, and then there will be homework. You can go homework questions too tomorrow if you want, but let's try and focus it on exam questions, just because I think that's the main purpose of that. So if you do have an exam question tomorrow, you guys are going to take a screenshot and post it in Discord. So we'll do that tomorrow, just because if you post them now, maybe they're going to get lost. So we'll post them tomorrow morning around 10:15 for you guys. Okay, so sorry I ran a little bit late. You guys are always free to say like, hey, stop it. You know, I want to go sleep. But yeah, I just got caught up. So cool. See you guys tomorrow. Again, that's totally optional. We're not doing anything new tomorrow. So if you want to sleep in instead, totally fine. I will not get offended. So, okay. See you guys. Take care.